In November of 2010, two physicists looked at the oldest light in existence and claimed they had found something printed beneath it. Not a galaxy, not a star, faint concentric rings scattered across the microwave glow that fills the sky. And they argued these rings were not noise, they were scars, the fading fingerprints of black holes that finished their work in a universe that died before ours was born. Hold that idea because of how strange it is. The light they studied is 13.8 billion years old, the boundary of everything we can see. And they were proposing that the boundary is not the beginning, that something leaked through it, that the cosmos you live in is one page in an endless book, and the previous page left ink behind. The model is called Conformal Cyclic Cosmology, and the rings carry the names of the two men who reported them, Vahe Gurzadyan and Roger Penrose, the latter a future Nobel laureate. These are the Gurzadyan-penrose rings, and the claim attached to them is among the most audacious in modern cosmology, that our Big Bang was not an origin, but a doorway. By the time the screen goes dark, you will understand what conformal geometry is and why it lets a universe forget its own size, what a Hawking point is and why a confidence of 99.98% collapsed to 87, why an evaporating black hole takes longer to die than any number we can name, and why this beautiful structure, examined honestly, points somewhere its own authors did not intend. If you find value in explorations like this, the subscribe button quietly helps these deep dives reach more curious minds. So, here is where it begins. To understand why anyone would claim the universe is older than its own beginning, we have to start not with the rings and not with the sky, but with a problem. A problem so old and so quiet that most people never notice it is there. The problem of order. Consider the room you are sitting in. Leave it alone for a year, and it does not become tidier. Dust gathers, things wear, heat spreads out and never gathers back. This one-way drift from order toward disorder, from structure toward sameness, is described by the second law of thermodynamics, and it is one of the most reliable statements in all of science. Physicists measure this disorder with a quantity called entropy. Entropy almost always increases. A hot cup of coffee cools to room temperature. It never, on its own, pulls heat back out of the room and reheats itself. Now scale that observation up to the entire universe. If disorder only ever increases, then run the clock backward. The past must have been more ordered than the present. And the deep past, the very beginning, must have been extraordinarily, almost incomprehensibly ordered. Low in entropy, to a degree that is difficult to put into words. This is where Roger Penrose enters the story, and we should pause on who he is, because the whole drama depends on it. Sir Roger Penrose was born in Colchester, England, in 1931. He is a mathematician first, a physicist second. And across 6 decades, he has produced work that sits at the foundation of modern cosmology. In 1965, he proved what is now called the Penrose singularity theorem, demonstrating with pure mathematics that under general relativity, the collapse of a massive star does not stop at a dense ball. It runs away all the way down to a singularity. That single paper is the reason black holes are taken seriously as physical objects. It is the work for which, in 2020, he was awarded the Nobel Prize in Physics, the committee citing the discovery that black hole formation is a robust prediction of the general theory of relativity. Hold on to that, because it produces one of the quiet ironies at the center of this story. The man whose mathematics helped anchor the Big Bang as the start of space and time is the same man who would later argue that the Big Bang was not the start of anything. We will return to that. In 1979, Penrose proposed something he called the Weyl curvature hypothesis. To understand it, we need one piece of geometry. When mass and energy bend space-time, that bending can be split mathematically into two parts. One part, called the Ricci curvature, is pinned directly to the matter present at a point. The other part, called the Weyl curvature, named for the German mathematician Hermann Weyl, is the free part. It is the curvature that can exist on its own, travelling, tidal, the stretching you would feel falling toward a black hole, the ripple of a gravitational wave. The Ricci part is fixed by what is there. The Weyl part is the geometry's own freedom. The Weyl curvature hypothesis is a single, severe statement. At the Big Bang, the Weyl curvature was effectively zero. The universe began geometrically smooth, gravitationally calm, with all its freedom unused. And this, Penrose argued, is exactly what low gravitational entropy looks like. Picture the difference between a still pond and a churning sea. The smooth Big Bang is the still pond, every ripple absent, every degree of freedom waiting. Over billions of years, gravity does what gravity does. It clumps. Matter draws together into stars, stars into galaxies, galaxies into clusters. And the ultimate expression of gravitational clumping is a black hole, the most disordered, highest entropy object the universe can make. The pond churns itself into a storm. So here is the puzzle in its sharpest form. Why did the universe begin in the still pond state at all? Out of all the ways a cosmos could start, the overwhelming majority are messy, high entropy, already churned. The smooth, ordered, low entropy beginning is astonishingly rare. The standard model of cosmology, the model called lambda CDM, with its cosmic inflation and its dark matter and its dark energy, describes the universe after this beginning with extraordinary precision. But it does not explain the beginning's strange smoothness. It assumes it. Keep that word in mind, assumes. We will need it later. Penrose found this assumption intolerable. A theory that simply helps itself to the most improbable starting condition imaginable and then declares the problem solved is not, to his mind, an explanation. And out of that dissatisfaction grew the most unusual idea of his career. The idea begins with a question about the far future, not the distant past. What happens to the universe at the end? The mainstream answer is bleak and well supported. The universe is expanding, and that expansion is accelerating, driven by what we call dark energy, represented in the equations by a positive cosmological constant, the Greek letter lambda. Galaxies are drifting apart. In the deep future, stars will burn out. Matter will fall into black holes. And the black holes themselves, over spans of time we will examine shortly, will evaporate away into faint radiation. What remains after everything is almost nothing. A thin, cold bath of photons and massless particles spreading forever into the dark. Cosmologists call this the heat death, the end of all events. And here, Penrose noticed something that most people would walk straight past. In that final state, the universe contains almost nothing with mass, almost nothing but light, radiation stretched and cooled toward zero. And a universe of pure radiation has a peculiar property. It has no way to tell scale. To measure size, you need a ruler, and to measure time, you need a clock. And rulers and clocks are built out of massive particles. A photon does not experience time or distance the way matter does. So, a universe of nothing but light, infinitely vast and infinitely dilute, becomes, in a precise mathematical sense, indistinguishable from a universe that is infinitesimally small and infinitely dense. Read that again, because it is the hinge on which everything turns. The cold, dead, infinitely large end of one universe is geometrically interchangeable with the hot, tiny, infinitely dense beginning of another. The end of time looks like the start of time. And if that is true, Penrose proposed, then it is not the end at all. It is a handoff. This is conformal cyclic cosmology. The word conformal is the key, and it names a specific kind of geometry. A conformal transformation is one that can stretch or shrink distances while leaving angles and the structure of light cones completely untouched. Picture a map of the Earth. On a flat map, Greenland looks enormous, as large as Africa, because the projection has stretched it. The true sizes are wrong. But the shapes, the angles of every coastline, the directions are preserved. That is conformal thinking. It keeps the shape and throws away the scale. The proposal, then, is that the universe runs in an endless sequence of what Penrose calls eons. Each eon is one complete cycle, from a hot Big Bang to a cold, infinite, radiation-only future. And the boundary at the end of one eon, its conformal infinity, is mathematically stitched directly to the Big Bang of the next, across a junction Penrose calls the crossover surface. The dying breath of one cosmos is the first instant of the one that follows. Forever. No first eon named, no last, an infinite chain. The mathematics that makes the stitch is captured in a single, deceptively simple expression. The new, rescaled geometry equals a factor, the Greek letter omega squared, times the old geometry. Spoken aloud, G tilde equals omega squared times G. Omega is the conformal factor, a number that can vary from place to place. Near the cold end of an eon, omega is driven towards zero, squashing the infinite expanse down to a finite junction. At the next Big Bang, it stretches the junction back open. The equation does only one thing, but it does it ruthlessly. It discards information about size, while preserving the causal skeleton, the light cone structure of everything that happened. Scale is forgotten, shape survives. And here is what matters. The positive cosmological constant, the same dark energy driving our universe apart, is not an inconvenience in this picture. It is required. It is what makes the far future boundary the right kind of surface to glue to the next beginning. Notice what this is meant to accomplish, because it is genuinely elegant. The low-entropy, smooth, still pond Big Bang is no longer an unexplained miracle. It is simply what the previous eon's death looks like after all its mass, and therefore all its gravitational clumping, all its black holes, all its disorder, have faded away and been smoothed by conformal rescaling into a calm, featureless surface. The Weyl curvature is near zero at the new beginning because the old universe spent an eternity grinding itself smooth. The puzzle of the ordered beginning dissolves. The theory proposes that the universe achieves its low-entropy start naturally, by forgetting. It is a beautiful answer. We will spend the final third of this exploration testing whether beautiful and true are the same thing. But a theory of this kind, however elegant, is only physics if it can be tested. And here Penrose and Gurzadyan made a bold move. They argued the previous eon should have left marks. Specifically, in the eon before ours, supermassive black holes would have collided and merged. Each merger releases a colossal burst of gravitational waves, energy radiating outward as a spherical pulse. And a spherical pulse from the previous eon, when it crosses the junction into ours, should imprint on our sky as a circle, a ring of slightly unusual temperature in the cosmic microwave background, the faint heat left over from our own Big Bang. The cosmic microwave background, the CMB, deserves a moment of its own, because it is the canvas on which this entire dispute is painted. It is the oldest light we can detect, released roughly 370,000 years after the Big Bang, when the universe first cooled enough for atoms to form and light to travel freely. It comes at us from every direction, nearly uniform, a temperature of about 2.7 degrees above absolute zero. But not perfectly uniform. There are tiny fluctuations, hot spots and cold spots, differences of a few parts in 100,000. Those fluctuations are the seeds of every galaxy that exists. And, according to the standard model, they are random, in a very specific statistical sense. The CMB is, as one set of critics would later put it, remarkably Gaussian and statistically isotropic. Random, even, featureless in any special direction. Gurzadyan and Penrose said, "Look closer." Gurzadyan here is the indispensable collaborator, and his expertise is unusual. Born in Yerevan, Armenia, in 1955, he is a specialist in chaos and dynamical systems, in the mathematics of randomness itself. He had spent years developing tools to measure how truly random a dataset is, including methods built on the work of the great mathematician Andrei Kolmogorov. If anyone had the instruments to find a faint, ordered pattern hiding inside a sea of noise, it was him. Using 7 years of data from NASA's WMAP satellite, the Wilkinson Microwave Anisotropy Probe, launched in 2001, they searched the sky for these concentric circles, regions where the temperature variation was unusually low, arranged in rings around common centers. And in 2010, they announced that they had found them. Rings of low variance, they reported, of up to 6 sigma significance. In the language of statistics, 6 sigma describes an event with a probability of less than 1 in 10 million of happening by chance. They cross-checked the result against data from Boomerang 98, an Antarctic balloon experiment, to rule out a flaw in the satellite itself. The circles, they said, were really there. Keep that number in mind, 6 sigma, 1 in 10 million. We will return to what happened to it. To feel the full weight of what conformal cyclic cosmology is claiming, we need to understand why black holes sit at the center of it. And for that, we need to understand entropy in its most surprising form. The intuition most of us carry is that disorder means a gas spreading out, a structure crumbling, things flying apart. But gravity inverts that intuition completely. When gravity is the dominant force, the most disordered, highest entropy configuration is not spread out. It is collapsed. It is a black hole. In the early 1970s, the physicist Jacob Bekenstein, working with insights soon sharpened by Stephen Hawking, proposed that a black hole has an entropy, and that this entropy is proportional not to its volume, but to the area of its event horizon, its surface. The relationship is written as a clean equation. The entropy, S equals K times C cubed times the area, A, divided by 4 times H bar times G. Spoken aloud, S equals K C cubed A over 4 H bar G. Here, A is the area of the horizon. K is Boltzmann's constant. C is the speed of light. G is Newton's gravitational constant. And H bar is the quantum of action. The details matter less than the consequence. Entropy lives on the surface, and it grows with the square of the black hole's size. Make a black hole bigger, and its entropy does not just grow, it explodes. This is why black holes dominate the entropy budget of the cosmos. Penrose estimated the entropy of the observable universe and found that the overwhelming majority of it is locked inside black holes. Picture an accountant auditing the books of the entire universe, every star, every galaxy, every cloud of gas, and discovering that nearly all the disorder, nearly all the entropy on the ledger is concentrated in a handful of dark, collapsed objects at the centers of galaxies. Everything else, all the light and warmth and structure we find beautiful, is a rounding error. Now return to the still pond and the storm. The Big Bang was smooth, low in gravitational entropy, vile curvature near zero. Across the life of an eon, gravity drives matter to clump, and clumping climbs toward its maximum in the formation of black holes. By the end, the universe's entropy is overwhelmingly bound up in these objects. And then, slowly, the black holes evaporate, carrying their entropy away as radiation, until the slate appears wiped clean. Conformal cyclic cosmology proposes that this evaporation, this final disappearance of the universe's mass, is precisely what allows the next eon to begin smooth again. The disorder does not vanish by magic. It fades out with the mass that carried it. And that phrase, fades out, conceals one of the strangest requirements of the entire theory. For the conformal trick to work, for the universe to truly forget its scale, mass itself must eventually disappear. Every massive particle must, in the unimaginably distant future, lose its mass and become, in effect, a kind of radiation. Penrose is explicit that this is necessary. If even a single type of massive particle survived forever, the universe would retain a ruler, a way to measure scale, and the conformal handoff would fail. So the theory demands that mass asymptotically fades to zero. Electrons, protons, everything. Sit with how large an assumption that is. There is no established physics by which a stable electron simply loses its mass and drifts away. And there is a sharper problem still. An electron carries electric charge, and charge, as far as we know, is perfectly conserved and cannot be carried by a massless particle in the ordinary way. To make mass fade while charge is conserved is, at present, an unsolved problem. The theory needs it to be true. Nature has not shown us that it is. We will return to this because it is one of the load-bearing walls of the whole structure, and it is built on ground no one has surveyed. This was the situation in 2010. A bold theory, an elegant geometry, and a claimed observation, the concentric rings, that seemed to confirm it. And then, within 3 weeks, the scientific community responded, and the response defined everything that followed. The dates are worth stating precisely because they show how science is supposed to work. On November 16th, 2010, Gurzadyan and Penrose posted their paper announcing the circles. On December 7th, just 3 weeks later, 2 independent groups posted rebuttals on the same day. One group was Adam Moss, Douglas Scott, and James Zibin at the University of British Columbia. The other was Ingunn Veihus and Hans Christian Eriksen at the University of Oslo. The next day, December 8th, a third analysis arrived from Amir Hajian. 3 independent teams, 3 separate analyses within 72 hours. And here is what they found, and it is subtle, so it deserves care. None of them said Gurzadyan and Penrose had made an arithmetic mistake. In fact, Veihus and Eriksen reproduced the ring structures exactly. The circles were really in the data. The disagreement was about what the circles meant. The critics ran simulations of a universe that contained only the standard, random Gaussian fluctuations the mainstream model predicts. No previous eon, no black hole echoes, just noise. And in that pure noise, they found the same kind of low variance rings. Moss, Scott, and Zibin wrote that the variation Gurzadyan and Penrose had highlighted was entirely expected in a sky which contains the usual fluctuations. Properly simulated random data, they said, contain just the sorts of variations claimed. The reason, they explained, is something hidden in the structure of the CMB itself. The temperature map has features on the same angular scale as the rings being searched for, and that structure guarantees that some low-variance circles will appear by chance, even in a sky whose fluctuations are completely random. The rings were real. The interpretation was the question. And 3 teams concluded the rings were consistent at the 3 sigma level with an ordinary, random universe needing no prior eon at all. This is the pattern you should watch for, because it will repeat. A striking signal is announced with a dramatic significance. Independent analysis reproduces the signal but reinterprets it as a natural fluctuation. The headline number shrinks. It happened with the circles in 2010. It would happen again on a larger stage 8 years later. Because Penrose did not retreat. He and his collaborators sharpened the prediction. If the previous eon contained supermassive black holes, those black holes would not only have merged, eventually, in the deep future of that eon, they would have evaporated entirely. And the evaporation of a truly enormous black hole, compressed by the conformal handoff into our sky, should leave not a ring, but a point, a concentrated spot, slightly warmer in its profile, marking where an entire collapsed monster from the previous world poured out the last of itself. They named these spots Hawking points, after Stephen Hawking, whose work on black hole evaporation made the prediction possible. To understand a Hawking point, you have to understand how a black hole dies and how long it takes. Hawking showed in the 1970s that black holes are not perfectly black. Through a quantum process at the horizon, they slowly radiate. The temperature of that radiation is given by another clean equation. The temperature, T, equals h bar c cubed divided by 8 pi gmk. Spoken aloud, T equals h bar c cubed over 8 pi gmk, where m is the mass of the black hole. Look at what that equation says. Temperature is inversely proportional to mass. The bigger the black hole, the colder it is and the slower it radiates. A small black hole is hot and dies relatively fast. A supermassive one is colder than the space around it and radiates with almost unimaginable patience. How patient? For a supermassive black hole of the scale Penrose's scheme requires, up to 100 trillion times the mass of the Sun, the time to evaporate completely is around 10 to the power of 106 years. Let me try to make that number real, knowing in advance that I will fail. It is not 106 years. It is a 1 followed by 106 zeros in years. The current age of the universe is about 10 to the 10th power years. The evaporation time is 10 to the 106th. The gap between them is so vast that calling the universe's entire history so far an instant, by comparison, dramatically understates it. This is a death so slow that the universe as we know it has not yet lived through the first imperceptible flicker of it. And the conformal handoff is supposed to take that 10 to the 106th year process and compress it through the rescaling into a single point of light at the dawn of the next world. What does it mean that the entire 10 to the 106th year death of a galactic cluster-sized black hole could be squeezed into a single warm spot a few degrees wide on our sky? Hold that question. It is the kind of claim that is either profound or empty, and telling the difference is the work ahead of us. In August of 2018, Daniel An, Christoph Meissner, Pavel Nurovsky, and Roger Penrose posted a paper making the case for Hawking points. The timing carried weight. Stephen Hawking had died that March, and the paper was dedicated to him. Using data from the Planck satellite, the European Space Agency's successor to WMAP, and specifically its 70 GHz frequency channel, they searched for these warm points and the characteristic way temperature should slope across them. The signature they looked for was a specific gradient, a linear change in temperature with distance from the center of each spot, captured by a precise statistical slope formula. And they reported a confidence level of 99.98%. They had started with 1,000 simulated skies for comparison, then extended to 10,000 to nail the number down. The spots they identified were striking. Some of the brightest had angular diameters of 3 to 4 degrees. For comparison, the full moon is about half a degree across. These spots were roughly 8 times the diameter of the full moon, and the brightest reached temperatures around 30 times the average fluctuation of the CMB. 99.98%. Remember the pattern. Remember the number. Because in 2019, Dylan Zhao and Douglas Scott, the same Scott from the 2010 rebuttal, examined the Hawking points claim and found the flaw they believed explained it. It was a statistical effect with an unglamorous name, the look elsewhere effect. The principle is simple, and it is one of the most important ideas in all of experimental science, so let me ground it. Imagine you are told that a particular person won a lottery, and that the odds of winning were 1 in 14 million. Astonishing if that one person was singled out in advance. But now imagine you searched through 14 million ticket holders looking for any winner. Finding one is not a miracle. It is expected. The improbability evaporates the moment you account for how many chances you gave yourself. Zhao and Scott argued that the Hawking points search had tested many different ring sizes, many scales, and that the headline confidence had not properly corrected for all those chances. When they marginalized over the ring size, accounting for the look elsewhere effect across the 52 scales that had been examined, the result transformed. The 99.98% collapsed to about 87%. In the language of statistics, that is roughly 1 sigma, the kind of fluctuation that happens routinely by chance. Their conclusion was stated without hedging. There is, they wrote, no statistically significant evidence for the presence of Hawking points in the cosmic microwave background. When the scales are properly marginalized over, they said, the evidence for an excess of Hawking points evaporates. They had used the Planck team's own cleaned map, the one called SMICA. There is a genuine technical disagreement buried here, and honesty requires naming it. Anne and his colleagues had worked primarily with the raw 70 GHz Planck channel. Zhao and Scott used the processed SMICA map. The two are not identical, and which one is the right place to look is itself a point of contention. But the core lesson stands, and it is the same lesson as 2010. A dramatic number, properly examined, shrank toward the mundane. The story did not stop there either. In a reanalysis published in 2024, a group applied machine learning, a neural network they called Hawking Net, built on an architecture named ResNet 18, to a full-resolution search of the CMB. They found that a few unusually bright or dark spots, just a handful of pixels, were skewing the results, erroneously generating regions that appeared to contain many low-variance circles. After accounting for them, they reported that no statistically significant low-variance circles could be found, and no significant evidence for Hawking points. Though, in fairness, they added an important caveat, that the absence of such features in currently available data does not disprove the model, but implies that higher resolution data would be needed to settle it. This is the honest state of the observational case, and we present it plainly. The central predictions of conformal cyclic cosmology, the rings and the points, have been reproduced as patterns in the data by multiple groups and reinterpreted as ordinary statistical fluctuations by multiple groups. The proponents maintain the signal is real and the critics' methods miss it. The critics maintain the signal is noise dressed up by the look elsewhere effect. As of now, the mainstream cosmological community has not accepted that the marks of a previous eon have been found. There is more to the theory than its sky marks, and the deeper we go, the stranger it becomes. Consider dark matter. We know from the way galaxies rotate and the way light bends across the cosmos that there is far more gravitating mass in the universe than the matter we can see. The Standard Model names this missing mass dark matter, but does not say what it is. Penrose, characteristically, offered an answer that follows from his framework. In 2017, he proposed that dark matter is made of particles he named Erebons, after Erebus, the ancient personification of darkness. An Erebon, in this picture, is a scalar particle with a mass around the Planck mass, the natural mass scale of quantum gravity. That mass is about 2.2 times 10 to the minus 5 grams, which sounds tiny until you realize it is around 21.8 milligrams, roughly the mass of a grain of sand, concentrated in a single particle some 22 orders of magnitude heavier than a proton. These Erebons, Penrose proposed, interact only through gravity, and they are not stable. They slowly decay, with a lifetime longer than the current age of the universe, releasing their energy as bursts of gravitational waves. He even speculated that some of the unexplained correlated noise in gravitational wave detectors like LIGO might, in principle, be Erebons decaying. No such detection has been confirmed. The Erebon remains a proposal, a particle required by the bookkeeping of the theory, not yet found by any instrument. And then there is the matter of B modes, which deserves telling because it is a cautionary tale the whole field absorbed. Conformal cyclic cosmology predicts that gravitational waves from black hole mergers in the previous eon should leave a particular twisting pattern in the polarization of the CMB, a pattern physicists call a B mode. The hunt for primordial B modes is one of the great quests of observational cosmology, because they would be a fingerprint of the universe's first instant. In March of 2014, a team running an experiment called BICEP 2 at the South Pole announced to enormous fanfare that they had found them, with a strength that disfavored the no-signal hypothesis at the level of many sigma. For a few months, it was hailed as a discovery of the century. And then it unraveled. By that June, the confidence was lowered. That September, a Planck analysis showed that ordinary galactic dust, the polarized glow of our own galaxy, could produce exactly the signal BICEP 2 had seen. In January of 2015, a joint analysis by the Planck, BICEP 2 and Keck teams delivered the verdict. The signal was dust. There was no detection of primordial gravitational waves. What does it mean that the most dramatic conformations in this field, again and again, dissolve under closer scrutiny into foreground, into noise, into the look elsewhere effect? It does not, by itself, prove any theory false. But it is a discipline of humility that the rest of this exploration will need. Spectacular signals are cheap. Signals that survive the prosecution are rare. So, we arrive at the end of the neutral presentation with the theory laid fully on the table. Conformal cyclic cosmology offers an elegant escape from the puzzle of the ordered beginning. It proposes infinite eons, each one's death conformally stitched to the next one's birth. It predicts rings and points in the ancient light, and a dark matter particle, and a twist in the polarized sky. Its observational claims are contested, but not closed. Its mathematics is genuine and beautiful. And resting quietly underneath all of it are three assumptions we flagged as we passed and promised to return to. That the conformal handoff is physically real and not merely a formula, that mass truly fades away, and that an endless chain of eons can stand in for a beginning. But before we put those assumptions on trial, we should see the company this theory keeps, and the deeper machinery it quietly rests upon. It would be a mistake to think conformal cyclic cosmology stands alone, a single eccentric idea at the edge of physics. It belongs to a whole family of models, a small tribe of cosmologies that all refuse to let the Big Bang be the final word on the beginning. Understanding that family clarifies what is genuinely distinctive about Penrose's version and what it shares with its cousins. The most prominent rival is the ekpyrotic model, proposed in 2002 by Paul Steinhardt and Neil Turok. Its picture is drawn from string theory. Imagine our entire three-dimensional universe as a membrane, a brain, floating in a higher dimensional space. And imagine a second brain floating parallel to it. The two brains drift together, collide, and rebound. And that collision is what we experience as the Big Bang. In the ekpyrotic and its later cyclic versions, this happens again and again, a cosmos of repeated collisions. Notice how different the mechanism is from Penrose's. The ekpyrotic universe bounces. It reaches a moment of contact and springs back. Conformal cyclic cosmology never bounces. It does not compress to a point and rebound. Instead, one eon expands forever into cold dilution, and its infinite, empty future is simply identified, conformally, with the next hot beginning. A bounce versus a handoff. Both refuse a single beginning. They refuse it in completely different ways. There are others in the tribe. Loop quantum cosmology, developed from the work of Abhay Ashtekar and others, takes the equations of the Big Bang and applies the rules of quantum geometry, and finds that the singularity is replaced by a bounce, a previous contracting universe rebounding into our expanding one. Earlier still, in 1993, Maurizio Gasparini and Gabriele Veneziano proposed a pre-Big Bang scenario, again rooted in string theory, in which a long, quiet, low-density era preceded the explosion. And further back, before any of these, sat the steady-state cosmology of the mid-20th century, which avoided a beginning altogether by proposing that the universe had always looked roughly as it does now, with new matter continuously created to fill the gaps as it expanded. That model died in 1964, when the discovery of the cosmic microwave background revealed a universe that was once hot and dense, a universe with a history, a universe that had clearly not always looked the way it does today. I mention steady state deliberately because it carries a lesson that hangs over this entire subject. It was an elegant idea, embraced by brilliant people, and it was killed by a single observation. The cosmic microwave background, the very light at the heart of the Gurzadyan-Penrose dispute, is the graveyard of one beginningless universe already. What does it mean that the same ancient light which buried one attempt to abolish the beginning is now the battlefield for another? Perhaps nothing. Perhaps only that this light has a way of holding theories to account. So that is the family. Bouncing brains, quantum rebounds, pre-Big Bang lulls, and Penrose's conformal handoff. Every one of them is an attempt to answer the same discomfort, the suspicion that a universe simply switching on, fully formed and exquisitely ordered, demands more explanation than the standard model provides. Keep that shared motive in view. These are not idle speculations. They are the work of serious physicists who feel, correctly, that the ordered beginning is a problem. We will see at the end that feeling the problem and solving it are not the same thing. Now let us return to Vahe Gurzadyan, because his particular genius is the part of this story most often overlooked, and it sharpens the central question of the whole dispute, which is not really about cosmology at all. It is about randomness. What does it mean to say a pattern is real, rather than an accident of noise? That is a mathematical question, and Gurzadyan spent his career on it. His tools come from the study of chaos and dynamical systems, and in particular from the work of Andrei Kolmogorov, one of the towering figures of 20th century mathematics. Kolmogorov developed a way to measure objectively how random a sequence of data truly is, a quantity now sometimes called the Kolmogorov stochasticity parameter. The idea, roughly, is that genuine randomness has a precise statistical fingerprint, and deviations from that fingerprint can be detected and quantified. Gurzadyan applied these methods to the cosmic microwave background, treating the entire sky as a data set to be interrogated for hidden order. Out of that work came a striking and underreported claim. Gurzadyan and collaborators argued, around 2011, that only a fraction of the CMB signal, on the order of 20%, actually behaves like a purely random Gaussian field, the kind the Standard Model predicts. The rest, they suggested, carries the fingerprints of the specific matter and structure the light passed through, making the sky not a clean sheet of noise, but what they called a weakly random universe. If true, it would mean the cosmic background is less featureless, less purely accidental than the mainstream picture holds. And here, predictably by now, the pattern repeated. Other analysts examined the weakly random claim. Sigurd Næss, among others, reported finding no evidence for any deviation from the Standard Model. The signal that Gurzadyan's randomness measures had flagged as special looked to other eyes and other methods entirely ordinary. Think about what this disagreement actually is. It is two camps staring at the identical sky, running different statistical instruments across it, and reaching opposite verdicts about whether what they see is pattern or noise. This is the irreducible heart of the matter. The data is shared, the interpretation is not. And no amount of staring at this one sky we have been given fully resolves it, which brings us to a limit we cannot engineer our way past. That limit has a name: cosmic variance. We have exactly one universe to observe, one cosmic microwave background, one sky. In ordinary science, when you want to know whether an effect is real, you repeat the experiment, you gather more samples, you let the noise average out. But there is only one observable universe. We cannot run it again. We cannot fetch a second sky to check the first. For the largest features, the ones spanning tens of degrees, we have a sample size of 1. And that imposes a hard, permanent uncertainty on every claim about whether a large-scale pattern is meaningful or a fluke. Picture a coroner asked to determine whether a single death was murder or misfortune, with no other case to compare it to, no pattern of similar deaths, just one body and one set of ambiguous marks. He can argue, he can analyze, but the certainty he wants is structurally out of reach. That is the cosmologist's position before the one sky we have. It is why these disputes do not resolve cleanly, and why they may never fully resolve at all. Let us anchor this in the real history, because it did not happen in the abstract. The cosmic microwave background was first predicted, then accidentally discovered, in 1965 as a hiss in a radio antenna that two engineers could not explain. The detailed measurement of its tiny fluctuations began in 1992, when the COBE satellite, NASA's Cosmic Background Explorer, first detected the faint anisotropies, the hot and cold spots, that would become the seeds of everything. That detection earned a Nobel Prize and opened the modern era. In 2001 came WMAP, mapping those fluctuations across the whole sky with far greater precision. Examining, in the Gurzadyan-Penrose analysis, more than 10,000 possible ring centers across the masked sky. Then, in 2009, the European Space Agency launched Planck, more sensitive still, releasing its great datasets in 2013, 2015, and a final analysis in 2018 that pinned the age of the universe at 13.787 billion years, give or take 20 million. Each instrument was a sharper lens on the same ancient light, and each, in turn, was handed the same impossible task: to decide whether faint rings and warm points in that light are messages from before time or the natural speckle of a single random sky. There is something humbling in this. The instruments grew sharper across 30 years, from Kobe's first coarse map to Planck's exquisite one. And the better the sky was seen, the more ambiguous its deepest question became. Greater precision did not settle whether the rings are real. It only refined the dispute. What does it mean that 3 decades of improving technology brought us no closer to deciding whether the ancient light carries a message from before our beginning or carries nothing at all but the grain of a single, unrepeatable sky? There is one more piece of Penrose's thinking that we have to place on the table, because it is heterodox in a way that matters enormously, and it sits at the foundation of his whole edifice. It concerns information and what happens to it inside a black hole. When matter falls into a black hole and the black hole later evaporates, a deep question arises. Is the information about what fell in, the precise details of every particle, preserved, or is it truly destroyed? For decades, this has been called the black hole information paradox. And over the last quarter century, the mainstream of theoretical physics has swung hard toward one answer. Information must be preserved. It is encoded somehow on the horizon and released in the radiation, a view tied to the holographic principle and to a framework called the ADS-CFT correspondence. The dominant consensus is that nothing is ever truly lost. Penrose stands against that consensus. He argues that information genuinely is destroyed in black holes, that the universe really does lose track of what fell in. And this is not a side opinion. Conformal cyclic cosmology depends on it. The whole scheme of an eon grinding itself smooth, shedding its disorder, arriving at a clean, low-entropy slate to hand to the next beginning, requires that the information and the entropy bound up with it can actually be removed from the books. If information is conserved, as the mainstream insists, the slate is never wiped, and the handoff has nothing clean to hand over. So Penrose has staked his cosmology on the losing side of one of the most consequential debates in physics. He may be right. The consensus is not proof. But understand the position the theory occupies. It does not merely propose new objects, the Erebons and the Hawking points. It requires that the prevailing view of black holes, held by most of the field, is wrong at its root. We will weigh what that costs in a moment. Let us also be concrete about the scale of the entropy we keep invoking, because the numbers are part of the argument. When Penrose first estimated the entropy involved in the universe's initial condition, in 1979, he arrived at a figure around 10 to the 88th in the natural units physicists use. As the role of supermassive black holes became clearer, that estimate climbed to around 10 to the 111th. And the maximum, the entropy the observable universe would have if every scrap of its matter collapsed into black holes, sits near 10 to the 123rd. That last number is the one that feeds the fine-tuning figure we will confront directly later, because the improbability of the ordered beginning is, in essence, the ratio between the tiny ordered slice the universe actually occupies and the colossal disordered phase space it could have occupied. The bigger that disordered space, the more astonishing the ordered start. And as the entropy estimates grew across the decades, the astonishment only deepened. What does it mean that the more carefully physicists counted the ways the universe could have been disordered, the more impossibly precise its actual ordered beginning became? The problem did not shrink with study, it grew. A word, too, on why the cosmological constant is not a detail here, but a requirement. The expansion of the universe is governed by the Friedmann equation, which relates the rate of expansion to the density of matter, the curvature of space, and that constant. In the far future, as matter dilutes toward nothing, the cosmological constant comes to dominate completely, and the universe settles into what is called a de Sitter state, expanding exponentially, smoothly, forever. And it is a specific feature of a universe with a positive cosmological constant that its conformal infinity, the boundary at the end of time, has exactly the geometric character, space-like, that Penrose needs in order to glue it to the next eon's beginning. Without dark energy, without that positive constant, the trick does not work. So, the same mysterious dark energy that the standard model struggles to explain, the energy of empty space, is in this picture not a problem, but a structural necessity. The acceleration tearing our galaxies apart is, to conformal cyclic cosmology, the very mechanism that smooths the way to the next world. Before we turn to judgment, two more chapters of the observational story deserve their place, because they show the ring claims were not a single event, but a sustained campaign. Between the 2010 circles and the 2018 Hawking points, the search continued. In 2013, Christoph Meissner, Pavel Nurovsky, and a collaborator reported ring-type structures in the WMAP data, at a confidence they put near 99.7%. Then, examining the newer Planck data, Anne, Meissner and Nurovsky reported ring structures again at around 99.4%, before the analysis evolved into the Hawking points method with its 99.98%. A lineage of claims, each refined, each impressive on its own terms. And running alongside that lineage, at every stage, the counter-lineage of reanalysis, reproducing the patterns and reading them as the ordinary structure of a Gaussian sky. Two parallel histories, the proponents and the critics, advancing in lockstep for over a decade, never quite meeting. I should say plainly, because it is easy to lose in the technical fog, that this entire idea begins from a place of real intellectual courage. The notion that our cosmos was born from the death of an earlier one is not a thing a lesser mind would dare to put before the world's cosmologists. That particular question, whether our universe is the child of a previous universe's long death, is one I have followed much further down its own road elsewhere, and it rewards the journey. But for now, we hold to the rings and the points, and to the moment we have been building toward, when presentation ends and examination begins. For we have now seen the theory whole. We have seen its motive, the ordered beginning that the standard model assumes rather than explains. We have seen its mechanism, the conformal handoff that lets a universe forget its scale. We have seen its predictions, the rings and the points and the Erebons. We have seen its family of fellow travellers and its dependence on the contested loss of information in black holes, and its need for the very dark energy that puzzles everyone else. We have seen the long, unresolved duel between those who find messages in the ancient light and those who find only noise. We have given it every fair hearing. The defence has rested. It is time, at last, to cross-examine. For the last stretch of this exploration, I have played the reporter. I have laid out conformal cyclic cosmology as fairly and as fully as I can, because a theory built by a Nobel laureate deserves nothing less than its strongest formulation before anyone tests it. Now the work changes. Now we cross-examine. And we begin by being precise about what is actually on trial, because most of this theory is not. The geometry is not on trial. Conformal rescaling is real mathematics. The Weyl tensor is real. Black hole entropy is real. The Planck data is real. None of that attacks the idea of a creator, and none of it will be debunked here, because debunking neutral science would be dishonest. What is on trial is a specific claim that often rides on the back of this theory, sometimes whispered, sometimes shouted. The claim that a universe like this one, cycling forever through infinite eons, removes the need for a beginning, and with it, the need for anything beyond the physical to explain why there is a universe at all. That claim, and only that claim, is the defendant. Let us call the first charge by its name. The claim is that an eternal cyclic universe has no beginning, and therefore needs no cause. If the eons stretch back forever, with no first one, then there was never a moment of creation, never an origin demanding an explanation. The chain simply always was. Present that argument in its strongest form, and it has real force. We feel the pull of it. An infinite past seems to dissolve the awkward question of what came first. But now examine it. And examine it not with theology, but with the mathematics of the very people who study these models. In 2003, 3 physicists, Arvind Borda, Alan Guth, and Alexander Vilenkin, proved a theorem that has hung over cosmology ever since. The Borda-Guth-Vilenkin theorem. Stated plainly, it says that any universe which has, on average, been expanding over its long history cannot be extended infinitely into the past. It must have a past boundary, a beginning. The condition is compact enough to write down. If the average expansion rate over the past history is greater than 0, the space-time is geodesically incomplete toward the past. Spoken aloud, average Hubble greater than 0 implies past incomplete. A geodesic is the path a freely moving object follows through space-time. To say the space-time is past incomplete is to say those paths cannot be traced back forever. They begin. Now here is the move that matters, and it is recent and it is decisive. One might hope that an exotic cyclic model like Penrose's slips through this theorem. It does not. In 2023, a team, William Kinney with collaborators Maiti and Sri Ram Kumar, applied the analysis directly to conformal cyclic cosmology and concluded, in their words, that the conformal cyclic extension of an asymptotically de Sitter universe is geodesically incomplete. Read that carefully. Even the infinite chain of eons has a past boundary. The cycles do not buy you an eternal past. They relocate the beginning, they dress it in new geometry, but they do not abolish it. And the architects of the theorem have said as much in plain language. Alexander Vilenkin, who is no theist arguing for a conclusion, has stated that the past history of the universe cannot be complete, and has expressed that he does not believe any viable cosmological model escapes a past boundary. This is not an apologist speaking. This is one of the authors of the theorem describing what his own mathematics requires. So what does it mean that the great attempt to escape the beginning, built by one of the most brilliant geometers alive, runs directly into a wall built by cosmologists themselves? It means the beginning does not go away by being hidden behind more cosmos. Stack 1,000 eons behind ours, stack an infinity of them, and the theorem still says the stack has a bottom. The question of the origin is not answered by this theory. It is merely pushed back one elegant step, and there it waits, exactly as insistent as before. Picture a man who owes a debt he cannot pay. He goes to a second lender to cover the first, and a third to cover the second, and a fourth to cover the third. As long as the chain continues, he feels solvent. He has always just borrowed enough. But no link in that chain ever creates a single coin of real wealth. Each one only passes the obligation backward. And if you ask whether the whole chain, taken together, has produced anything that pays the debt, the answer is no. It has only deferred it. An infinite regress of eons is that chain of borrowed cosmoses. Each eon hands the question of existence back to the one before it. None of them ever pays it. The debt of explanation is never settled. It is only passed back, forever, to a lender who, the theorem says, must eventually not be there. There is a deeper version of this point, and it survives even if you doubt the theorem. So let me state it carefully, because it is the strongest thing in this entire examination. Suppose, for the sake of argument, the eons really did stretch back with no first member. The theory would still be silent on the only question that ultimately matters. Why is there a sequence of eons at all? Why is there anything rather than nothing? Conformal cyclic cosmology is a magnificently detailed account of how one state of the universe transitions into another. It is a description of transitions. It is not, and was never designed to be, an account of why the whole system exists to do any transitioning. A perfect description of how the dominoes fall tells you nothing about why there are dominoes, or a table for them to stand on, or a world in which tables can exist. The theory operates entirely inside the universe. The question of why there is a universe to operate inside is not a question it can reach, no matter how many eons it strings together. That brings us to the second charge, and it is more intimate because it concerns the very problem Penrose built the theory to solve. The claim is that the low-entropy, exquisitely ordered beginning of our universe is explained naturally by the conformal handoff, so no fine-tuner, no deliberate setting of conditions is required. The previous eon ground itself smooth, the reasoning goes, and handed us a calm beginning for free. Give the argument its due. It is genuinely clever. It tries to convert the most improbable feature of our universe into an automatic consequence of geometry. But now, apply pressure at 3 points and watch what happens. First, recall the number that started Penrose down this road in the first place. He estimated the precision of the universe's initial low-entropy condition, and the figure he arrived at is one of the most staggering quantities ever written in a serious physics book. The probability of the universe beginning in a state as ordered as ours, he calculated, is roughly 1 part in 10 to the power of 10 to the power of 123. Spoken aloud, 1 over 10 to the 10 to the 123. Let me be clear about what kind of number that is, because ordinary language has no grip on it. It is not 1 in a trillion. It is not 1 in a Google. The exponent itself, 10 to the 123, is already a number larger than the count of every particle in the observable universe. And that monstrous number is merely the number of zeros in the denominator. You could not write this number out if you used every particle in the cosmos as a single digit. It dwarfs a Googleplex. That figure is Penrose's own. He is, by his own clear statement, an atheist. He does not offer this number as evidence for a designer. He offers it as the measure of the problem he is trying to solve. But look honestly at what the number is. It is the signature of precision so extreme that the word coincidence loses all meaning in its presence. Take a moment with this, genuinely. If you encountered a single lock with that many possible settings and you found it set, on the first try, to the one combination that permits a universe of stars and chemistry and conscious minds capable of asking about it, what would you conclude? That it fell that way by accident? The honest mind balks. Precision of this order does not whisper of chance. It speaks of decision. And a decision requires something that can decide. Now, the theory's response is that the conformal handoff explains the precision away, that we need not posit a chooser because the geometry delivers the low-entropy start automatically. So examine whether it actually does. And here we find that the explanation rests entirely on the two assumptions we flagged and set aside. It requires that all mass fades to zero, so the universe can forget its scale. And it requires that gravitational entropy effectively resets at the crossover, so the new eon can begin clean. Neither of these is established physics. The mass fade-out, as we said, has no observational support whatsoever, and runs into the wall of charge conservation for the electron and the proton. Even sympathetic critics see this clearly. The physicist Sabine Hossenfelder, examining the theory, described it as a very elegant theory, with the only ad hoc assumption being the asymptotic vanishing of the mass. Hear what that means. A friendly observer, looking for the single weak joint in the structure, points straight at the assumption the entire entropy explanation depends on. The theory explains the fine-tuning of the beginning only by assuming a process for which there is no evidence and a serious obstacle in known physics. That is not removing the fine-tuning, that is relocating it into an unproven mechanism. And the entropy reset faces a problem of its own. A quantum information analysis has argued that Penrose's required loss of information in black holes is not compatible with the standard quantum notion of entropy, and that this undermines the very idea of an entropy renormalization needed to match the two sides of the crossover. In other words, the bookkeeping that is supposed to make the handoff balance may not balance at all. So the second charge fails. The claim was that conformal cycling explains the ordered beginning and dispenses with a fine-tuner. But the explanation works only if you grant it two unverified miracles: the fading of mass and the resetting of entropy. And it never touches the 1 in 10 to the 10 to the 123 precision, except to push it inside machinery no one has observed. The fine-tuning does not dissolve. It is moved to a place where it is harder to see. What does it mean when a theory can only explain an extraordinary precision by assuming an even more extraordinary and entirely unobserved set of processes? It means the precision was never explained. It was relocated. The third charge is the quietest and the deepest. It is the claim that the universe forgets itself and is reborn with no external cause at all. That the cycle is fully self-contained, a perpetual machine needing nothing outside it. And to test this one, we have to look hard at the word that does all the work in this theory: forget. When Penrose says the universe forgets its scale, he means something exact and mathematical. He means that in the conformal rescaling, the information about size is discarded by the equation, while the angles and causal structure are preserved. That is a true statement about the mathematics. But notice the leap that happens next. From the fact that the equation forgets scale, the theory concludes that the physical universe forgets scale, that the cold, infinite end of one eon literally becomes the hot, dense beginning of the next. And that leap, from a property of the formula to a claim about reality, is asserted, not demonstrated. Whether the remote future of one eon physically is the next Big Bang, or is merely mathematically identical to it on paper, is unresolved even among those sympathetic to the idea. Consider an everyday version of this, because the gap is easy to feel once you see it in human terms. Imagine a translator who takes a long, detailed letter written in one language and renders it into another. A good translation preserves the meaning, the relationships between the ideas, the shape of the argument, while the original words, the specific letters and sounds, are discarded entirely. In that sense, the translation forgets the original language. Now suppose someone told you that because the translation forgot the original words, the original letter therefore wrote itself, that no author was ever needed, that the meaning simply passed from one language to the next on its own. You would see the error instantly. The translation, preserving meaning across a change of form, tells you nothing about where the meaning came from. It tells you nothing about whether there was an author. The conformal map is exactly this kind of translation. It carries causal structure across the junction between eons while forgetting scale. And the claim that this forgetting makes the universe self-creating, that it needs no author, is the same error as the self-writing letter. The mapping describes how the message is carried over. It says nothing about why there is a message or a mind to mean it. This is where the everyday picture and the cosmic claim part ways. And the place they part is precisely the place the argument for a self-sufficient universe breaks. The translation always traces back to an author. The letter never wrote itself. And a universe that elegantly carries its causal structure from one eon to the next still has, sitting underneath it, untouched and unanswered, the question of why there is any structure, any law, any eon, anything at all to be carried. There is a fourth charge, subtler than the others, and it concerns not whether the theory is true, but whether it is the kind of thing that can be tested at all. A theory earns the name science by making predictions sharp enough that the world could prove them wrong. So ask honestly, what would prove conformal cyclic cosmology wrong? Consider its predictive record. First, the signature was low-variance concentric circles, announced at 6 sigma. When 3 teams read those as ordinary noise, the emphasis shifted to Hawking points, announced at 99.98%. When that confidence was shown to collapse under proper statistics, the predicted signatures, as the critics noted, had themselves changed since the theory's first proposal. There were B modes too, which dissolved into galactic dust. And when the most recent analysis found nothing significant, the response was that the absence of these features does not disprove the model, only that higher resolution data is needed. Now, that last statement is reasonable on its face. Better data often is needed. But notice the shape of the reasoning, because it should sound familiar. The same physicists who reject the multiverse as unscientific on the grounds that no observation could ever confirm or deny it, must ask whether their own framework is drifting toward the same condition. When every confirming signal is reinterpreted as noise, and every null result is met with the promise that a future telescope will vindicate the theory, at what point does a chain of deferred confirmations become indistinguishable from faith? This is not a charge unique to Penrose. It is the precise objection cosmologists themselves level at the multiverse, the idea that infinite, unseen universes explain our fine-tuning. They call it speculation dressed as science, because no possible measurement could falsify it. The honest mind has to apply that same standard evenly. A theory invoked to remove the need for a creator cannot itself be exempt from the demand that it be testable. If the multiverse fails the test of science, A beginningless cosmos, whose every prediction has so far either vanished or been deferred, cannot be waved through unexamined. Take a moment with that double standard, because it calls for your own judgment, not mine alone. If a theory that predicts unobservable universes is rejected as metaphysics, what should we say about a theory whose observable predictions keep receding toward the edge of detectability? Answer that honestly, and you have already seen the shape of the problem. Let me put the whole prosecution into a single frame by turning a favourite accusation around. Critics of theism love a phrase. They call it the God of the gaps, the habit of inserting a creator wherever science has not yet explained something. It is a fair warning against lazy reasoning. But watch what conformal cyclic cosmology requires, and ask who is filling gaps. To make the theory work, one must posit Erebons, never detected, a fade-out of mass, never observed and obstructed by known physics, an entropy reset, contested at the level of basic quantum theory, a physical identification of one eon's death with another's birth, asserted beyond what the mathematics shows, and signatures in the sky that three independent teams read as ordinary noise. That is a great deal of unobserved machinery invented precisely to avoid a particular conclusion. If inserting an unseen cause to plug an explanatory gap is a sin, then the gaps here have been filled many times over with entities far less evident than the one the theory was built to avoid. I want to be careful and fair here, because Roger Penrose is not a charlatan, and conformal cyclic cosmology is not a fraud. It is a serious, creative, mathematically rich attempt by a great mind to answer a real and profound question: why the universe began in such an ordered state. The question is legitimate. The dissatisfaction that drove it is one every thinking person should share. The mainstream model really does assume the ordered beginning, rather than explain it. Penrose was right to be bothered. He was right that something needs accounting for. Where the evidence parts from the conclusion is in the answer. The theory does not remove the beginning because the theorem forbids it. It does not remove the fine-tuning because it only buries it in unobserved mechanisms. And it does not explain why anything exists, because no description of transitions ever can. So follow the evidence where it actually leads. We have a universe that, by the mathematics of cosmologists themselves, had a past boundary, a beginning. We have an initial condition of a precision so extreme that the word chance cannot survive contact with it. We have a structure of laws and order that unconscious matter, left to itself, does not produce. A beginning that demands a cause, a precision that points to a choice, an order that implies a mind. These are not the leftovers of a failed theory. They are the stubborn facts the theory tried and failed to explain away. And when a cause is required, and the cause must be outside of time and space because it brought time and space into being, and it must be of staggering power because it set the scale of a cosmos, and of staggering knowledge because it set the constants for life, and possessed of will because a choice was made among unimaginable alternatives, then we are no longer describing unconscious matter. We are describing exactly what every age before our own would have called, without hesitation, the Creator. This is the part that stays with me. Not the scale of the eons, vast as they are, the precision. A universe poised at its first instant on a setting 1 part in 10 to the 10 to the 123 away from sterile chaos. And it landed on the one that lets minds exist to notice. Precision requires decision. I return to that often, not because it is comfortable, but because every attempt I have watched to escape it, including the most beautiful one in modern cosmology, has ended by pointing back at it. Let me bring this exploration to a close. We began with a problem older and quieter than the rings, the problem of why the universe started in a state of such extraordinary order, its vile curvature near zero, its entropy impossibly low. We followed Roger Penrose, the man whose own mathematics helped anchor the Big Bang, as he tried to answer that problem by abolishing the Big Bang as a beginning. We watched conformal cyclic cosmology unfold, the infinite eons, the conformal handoff that lets a universe forget its scale, the Gurzadyan-penrose rings in the WMAP sky, the Hawking points in the Planck data, the Erebons proposed to be dark matter, the long story of confidence levels announced and then quietly reduced. 6 sigma fell to 3, 99.98% fell to 87. And underneath the contested observations sat 3 assumptions the theory could not pay for: the reality of the handoff, the fading of all mass, and the dream of an eternal past. And when we tested those, the evidence did not vanish into the eons. It sharpened. The Borde-Guth-Vilenkin theorem, applied directly to conformal cyclic cosmology, returns the beginning the theory tried to remove. The fine-tuning of 1 part in 10 to the 10 to the 123 is not explained, only relocated into machinery no instrument has seen. And no chain of cycles, however infinite, can answer why there is a chain at all. A beginning that requires a cause, a precision that requires a choice, an order that requires a mind. The most elegant escape modern cosmology has offered ends by pointing exactly where it set out to avoid, toward an eternal, uncaused, intelligent cause, with power and knowledge and will. The evidence, followed honestly, leads in one direction. If you found value in this exploration, consider subscribing. It helps these deep dives reach more curious minds. And there is a thread here I have only half pulled. We spent this hour asking whether anything came before our Big Bang, and treated that prior eon mostly as a source of marks in the sky. But the idea that our entire cosmos was born from the death of an earlier one deserves its own full reckoning, and I have followed that question much further than I could today. If it has its hooks in you now, you will find where on the end screen and in the description below. The rings may be only noise. The Hawking points may be only the look elsewhere effect dressed as discovery. The eons may never have existed at all. But the question they were invented to answer does not fade out the way the theory says mass must. Whether or not the universe forgets, the question of its beginning remains, patient and undimmed, waiting for an honest answer in the oldest light there is. Good night.